Hello everyone. In this video, I'm going to provide an overview for Section 1, which covers outcomes, events, and sample spaces. So the overview breaks down really to 4 topics. We'll talk about basic properties of sets, sample spaces, events, and the important principle of inclusion-exclusion. So we begin our discussion of set properties with a very fundamental set operation. Suppose that A and B are sets. Then the union of sets is denoted by A with this little symbol that looks like a U and a B. So this is the union of sets. And here's a nice, easy example. We could see if A contains the elements 1, 2, 3, B the elements 3, 4, 5, then A union B would be 1, 2, 3, 4, 5. And this green shaded area represents A union B. Another important operation is the intersection of A and B. And so here you could see that the symbol looks like an upside down U. And these are the elements in A and B. So for a simple example, you would see the intersection is this red section where the two sets overlap. So now if A is the set 1, 2, 3, 4, B is 3, 4, 5, 6, A intersects B would be the set 3 and 4. So those are the elements that are in A and in B. And the last operation on this slide is the complement. We say that, a complement is the set of elements in S, where S might be a universal set or sample space, minus or take away the elements in A. So this is a complement. In our textbook, it'll be denoted by A with a superscript C. Other times you may see it denoted like this, A with a bar on top. And just as a visual, you could see that if the square is your universal set, then a complement would be this red area, right? Assuming this set in here is A. A few more set properties. Very important property here is De Morgan's law, which says if you take the complement of the union, that's equal to the intersection of the complements. Okay, so notice you have to sort of interchange union with intersection here. And if you start with E intersect F, you take the complement of that, that becomes the union of the complements. So you can try to see some of these things here. If I have A union B as these two sets shaded in blue, then A union B complement would be this sort of turquoise colored area, which is A complement intersected with B complement. Another important idea is that of a subset. We say a subset of S is a set that's contained in S. So it's simply a set within a set. So here we would say that A is a subset of B. And one more important property of sets, this will come up in probability and anytime we need to do some counting. If S is a set with n distinct elements, then there are 2 to the n subsets of S. But notice this 2 to the n includes the set S itself and the empty set. So n distinct elements, and there's 2 to the n subsets of S. Okay, now a couple of important definitions. Let's say we have some type of experiment that generates data. Then the sample space, denoted by S, is a set of all possible outcomes of the experiment. Now, one experiment may have different sample spaces, at least different possible sample spaces, so you need to be clear sometimes how the sample space is to be defined. Okay, another definition is that an event E is simply a subset of S, and this might be denoted using this notation. Think of this as E is contained in or possibly equal to S. So here are some examples. So the first one, suppose an experiment consists of having a baby. Then a possible event might be that the baby is a boy. So here we could say our event E is just equal to B, okay, B for boy. And this would be our event. Let's say the sample space is B or G. So these are the two outcomes, and you could see our event is a subset here. As a second example, let's suppose that an experiment consists of tossing two coins. Then a possible event would be that the outcome is the same on both tosses. So we could identify our event E as being the outcome HH for two heads and TT for two tails. So this would be an event, and let's say the sample space consists of all possible outcomes here, where we're sort of implying here that order is important. So we get HH, HT to be thought of differently as TH and then TT. Third example, let's say an experiment consists of measuring the lifetime of a light bulb. Okay. Then consider the event that the light bulb burns out by 3.2, suppose this is, hours or some unit of time, so 3.2. So our sample space can be described using interval notation. So here we have a time 0 up to 3.2, and we could say the sample space goes from time 0, and there's no upper bound, so we just simply write infinity as positive infinity. You might notice here that here we have continuous data, okay, whereas in the first two, we could say that this is discrete data. And the last piece of this section is the principle of inclusion-exclusion, which is sometimes abbreviated as pi. Okay, so the idea behind inclusion-exclusion is that you want to count or at least calculate probability of A union B. And so the idea is you first look at the probability of A plus the probability of B, okay? And this could also apply for the number of elements in A union B. So the idea here is that you count everything in A and you count everything in B. Now, by doing that, there are some elements that you've included in both of these, right? In fact, if anything is in the intersection, you've actually counted it twice. So now you need to subtract off what's in the intersection. So we include it here, and then we have to exclude it here. That's why this is called the principle of inclusion-exclusion. So you could see here, we're counting everything in A and then everything in B. So we've counted this overlap twice. That's why we have to subtract off the intersection. And you could see it follows easily from this principle up here that if A and B are mutually exclusive in the sense that they don't have any intersection, right? Our picture would look something like this. Then the probability of A union B is equal to the probability of A plus the probability of B. And so this term here we don't have to worry about because the intersection is the empty set. So this term just drops out. And this is an important principle which can be extended to 3 sets. You can see here's what it looks like when you want to find the union of A, union B, union C. It's possible to draw this, right? We just have a Venn diagram with 3 sets. And notice the point where they all overlap. That's A intersect B intersect C. And one way to try to remember this is if you want, let's say, either a count of elements, or this will apply for probability, the probability of A union B union C. You find the probabilities of each of these sets individually, and we've added. But by doing this, we've counted various overlapping areas, more than once. So we add up all the probabilities of the individual sets. Then we have to subtract off all the two-way intersections, right? There's 3 of them, minus A union B, minus B union C, minus C union A. But now we've actually subtracted off too much, and so we have to add back the probability of the intersection. So again, a very important principle. This can be extended even more. You could extend it to 4 sets or even more than 4 sets. But we will restrict ourselves. Most problems will be either 2 or 3 sets. It's rare. There might be 1, maybe 2, but not many problems where you actually have 4 sets. Okay, this includes the video.